All right, it's on. Okay, so today is the lecture number 3 of our course, and today we're gonna discuss the eigenstates and eigenvalues of a matrix, inverse matrices, in unitary matrices, and the Hilbert space. And probably we will even start discussing the concept of a qubit, because it relates to the concept of Hilbert space. Essentially, a qubit is a qubit is given or described in the Hilbert space of dimension 2. All right, so but essentially we're gonna continue this list of matrix properties. And so it was the property number 5. Let's continue this list, and it's gonna be property number 6. It's not property, but we still learning how to work with the matrices. And this item number 6 is eigenstates and eigenvalues, eigenstates or eigenvectors. Let's write this eigenvectors. Eigenvectors and of a matrix. Eigenvectors and eigenvalues of a matrix. So these are central concepts in quantum, right? Because as we will see, eigenvalues they represent the states that a quantum system can have or acquire, and eigenvectors they became eigenstates. So these are the states of a quantum system. So the quantum system can be found only in these states, but not in others. This is the importance of these eigenstates and eigenvalues. But from the mathematical point of view, what is eigenstates? So let's start from eigenstates. So the eigenstate or eigenvector, right? Eigenvector. So so as we say, a matrix, like let's call it C, for example, right? A matrix can be described as a operation that acts on a vector and it creates another vector. For example, my matrix or operator C acts on vector X and it creates another vector Y, right? In the component representation, the same can be written like this: Cij xj, and it creates yi, right? And the summation runs over j. So this is basically the same thing. So geometrically, what it means that initially we had a vector like vector x, and then after applying this matrix C, we obtain another vector, something like this, like for example this. So this is cx or y. So that's a new vector. So it changed in length. It rotated by an angle. So basically another vector in the same space. But for any matrix, there is a vector that when you apply this matrix C on this vector, it creates another vector which is parallel to the initial one, and this is what is known as eigenvector. So let's write it down like so a matrix, and for example, our matrix C has vectors x that cx are parallel to the initial one, to this vector x, and these are eigenvectors. All right. So what it means that the application of this matrix or operator on this vector creates another vector in the same direction, but probably changed in length. It means that in the output we get the same vector, but multiply by this scaling factor lambda. Okay. And this lambda is eigenvalue or eigenvalues of the matrix. So value alpha, lambda is the eigenvalue or values. Usually we have, for example, for two-dimensional space, for two-dimensional vectors, we get two eigenvalues, unless they are the same. And let's know that if this matrix C is singular, right? So if the matrix is singular, it means that the eigenvalue is equal to 0. Okay, so we have this equation over here, Cx equals to lambda x, and we need to find the vectors x, the eigenvectors and eigenvalues, and how we do so. So to find the eigenvalues and eigenvectors, we use the characteristic equation to find the eigenvalues and eigenvectors. We use the characteristic equation. So basically, we obtain the determinant So we basically use this this property of the determinant being the invariant. So our matrix then minus minus lambda I and V equal to 0. So this is the characteristic equation. The lambda is the eigenvalues of the matrix. I, of course, is the identity matrix. Identity matrix, which is the same as delta Kronecker, Mn, you remember, right? So it's 1 on the main diagonal, and the other elements are 0. Something like this. Identity matrix. So the best way to understand how this works, let's consider a problem. So problem number 1. Let's take a very simple matrix like 3, 1, 2, 4, for example. Right. Very simple matrix in the two-dimensional space. Yeah, and the problem is to find the eigen vectors and eigen values. Okay. So to write down this characteristic equation, we need to find this construction C matrix minus lambda I, right? So our matrix is 3, 1, 2, 4, then minus lambda and unitary matrix in the same space, which is 1, 0, 0, 1. Okay, which gives us 3 minus lambda, then 1, then 2, and finally 4 minus lambda. So this matrix like this, and we need to find the determinant of such a matrix. So determinant of this matrix, 3 minus lambda, 1, 2, 4 minus lambda, is equal to the product of the components on the main diagonal, which is 3 minus lambda times 4 minus lambda, minus the product of the components of diagonal, which is minus 2, right? Equal to 0. This is the characteristic equation for in this case. So let's expand the parentheses. We got 12, then minus 3 lambda, then minus 4 lambda, and then plus lambda squared minus 2 equals to 0. So it gives us lambda squared minus 4 lambda, minus 7 lambda, and plus 10 equals to 0. Okay, so the lambda 1, 2 is minus b, which is 7, plus minus square root of b squared, 49, minus 4 times 10 over 2, right? So it is equal to 3, so 7 plus minus 3 over 2, which gives us lambda 1 to be 5, and lambda 2 to be 2. So these are eigenvalues of our matrix C, right? 5 and 2 eigenvalues. So we've got two eigenvalues, and hence we get, or we can write the two equations for eigenvectors. For two equations for eigenvectors. So it's gonna be C x1, which is the first eigenvector, equals to lambda 1, which is 5 in our case, times x1, right? And the second one is C x2 vector lambda 2 x2. So now we know this x1, we know this lambda 1, lambda 2, and in each of these equations, the only unknown is the vector itself, and we can easily solve these equations and find the eigenvectors. So let's rewrite this in this way. I mean the first equation. So C matrix x1 vector minus lambda 1 x1. So now I want to so x1 here and here is common, and I want to take it out from the parentheses to factorize this, right? So it's, but I need to rewrite this term before x1 in this in the second term. So I write as C x1, and then I can represent this as lambda 1 times identity matrix and x1, right? Identity matrix multiplied by any vector gives the same vector, so it doesn't affect anything. But at the same time, it allows us to rewrite this as a C matrix C matrix minus lambda 1 I times x1, and this is supposed to be equal to 0. Okay, so this is our equation, and now we can go and substitute the matrix, the eigenvalue, and unit and identity matrix in this equation. So our matrix is 3, 1, 2, 4, 3, 1, 2, 4, right? Then minus lambda 1 is 5, and identity is 1, 0, 0, 1. Okay, so it is equal to 3 minus 5. 3 minus 5 is minus 2, then 1, then 2, and 4 minus 5 is minus 1, right? So, and this matrix multiplied by, where is it? Multiplied by the vector x1 with components x1a and x1b, right? We have two components for the first vector, is equal to 0. All right, so we use the matrix rule for the product, which gives us minus 2 x1a plus 1 x1b equal to 0, and second one is 2 x1a minus x1b. So the two coincide, they are the same, right? And in this case, it means that for x1b, we can take any number. I mean, usually we take the just one unit, right? So we assume x1b is 1. And that means that for the x1a, we get x1a is equal to 1/2, right? Yeah, 1/2. So it means that x1 vector is 1/2 and 1, these components, right? So this is the first eigenvector of our matrix. Let's go and find the second one, the second vector. So again, our matrix is 3, 1, 2, 4, 3, 1, 2, 4. Then minus the second eigenvalue is 2, 2, and identity 1, 0, 0, 1. Okay, this gives us 1, 1, 2, and 2. Matrix. Okay, 1, 1, 2, 2 multiplied by the components of the second vector, just x2a, x2b equal to 0. And again, we obtain two identical equations, which are x2a plus x2b equal to 0. We assume that x2b is equal to 1, and hence x2a is equal to -1, -1. So the second vector, second eigenvector is -1 and 1. This is the second vector. Okay, so this is more or less the procedure of finding the eigenstates and eigenvalues, eigenvectors and eigenvalues of a matrix or operator represented in the matrix form. Okay, also let's define if the vectors are orthogonal or not. Are the vectors orthogonal? Are they orthogonal? To do so, we need to take the inner product, right? So the first one was 1/2 and 1. So x1 vector times x2 vector. We write the first one as the row, 1/2 and 1. The second as a column, -1 and 1. Right? 1/2 times -1 gives us -1/2. Plus 1 times 1 gives us 1. So the answer is 1/2. So the vectors are not orthogonal. Not orthogonal. For this particular case, for this particular matrix, the eigenvectors are not orthogonal. And I mean, they are not bound to be orthogonal for an arbitrary matrix. But today we will discuss the type of a matrix for which the eigenvectors are always orthogonal. And finally, as a practice, let's normalize these vectors, because usually we represent the vectors in quantum in the normalized way. So, for example, x1 absolute value, right? Absolute value for the vector x1 is 1/2 squared plus 1 squared, which is 1/4 plus 1, which is square root of 5 over 2, right? And x2 absolute value is minus 1 squared is 1 plus 1, so it's square root of 2. So the normalized vector 1 and normalized is equal to we need to divide, right? So it will be 2 over square root of 5 vector 1/2 and 1, and second vector normalized normalized is equal to 1 over square root of 2 minus 1 and 1. Okay. So normalized vectors, they just denote the direction in space, in this two-dimensional space, rather than anything else. Yeah, normalized vectors. And these vectors are not orthogonal. All right, so last week we introduced the concept of Hermitian matrix, and a Hermitian matrix is a matrix after Hermitian conjugation, right? And now let's consider the main properties of Hermitian matrices. The main properties of Hermitian matrices. So basically, yeah, and why they are interested for quantum? There are two of them. The first one is that eigenvalues of Hermitian matrix are real values, valued values of Hermitian matrix are real valued. And second one is that eigenvectors of Hermitian matrix matrices are orthogonal or linearly independent. Eigenvectors of Hermitian matrix are orthogonal or linearly independent. What it means? It means that one can use the eigenvectors of Hermitian matrix to span the basis, right? So we can use them to represent a basis. Represent the basis, and then use this basis to describe that space. And of course, for one space, there are infinite number of different Hermitian matrices, and all of them have different eigenvectors, and this simply means that there is an infinite choice of basis vectors to represent the same space. Yeah, let's write this like this: x for two-dimensional space. So for two-dimensional space, the first eigenvector Hermitian, right? If I take the product of it with the second one, Hermitian, it's equal to 0. Right. So when the inner or dot product is equal to 0, that means that the projection of one vector on another one is equal to 0. The vectors are orthogonal. But there is a important point here is that for complex spaces, right? For example, for the I mean, some time ago we discussed these matrices with complex components. They are of course defined in the complex space, and the vectors also can be complex in the complex space. And when we take the inner product of two complex vectors, we have to put the complex conjugation to the one of them. So we, for example, define the scalar product of vector by itself properly. Instead of getting the complex number, we get the real number. So we have to remember about this. When we generalize the scalar product to the complex space, we have to put this complex conjugation operation in the inner product. And this is the definition basically of the two orthogonal complex vectors. And again, I repeat that the eigenvectors of a Hermitian matrix are orthogonal and can be used to represent, to span the basis of the corresponding space. Okay, let's consider another problem or another example here. At this part, it's very easy to generate these problems and examples. And yeah, for example, yeah, let's prove, or let's show, for example, that the eigenvalues and eigenvectors of this simplest Hermitian matrix with components 1, I minus I, and for example 2, right? So this is the simplest ever possible Hermitian matrix. Hermitian, why it's Hermitian? Right, because complex conjugation gives us minus here and plus here, and then when you coincides with the initial matrix. By the way, do you hear me well?
Yeah.
It says on my side, it says that the internet connection is unstable, probably because of the weather. All right, so this is our matrix, and let's find the eigen states and eigenvalues and demonstrate that they fulfill these Hermitian matrix properties. The eigenvalues are real, eigenvectors are orthogonal. Okay, so to do so, we write the determinant of the characteristic equation. So now I write this. I mean, I skip the formation of this matrix, so it's 1 over 1 minus lambda, then I, then minus I, and then 2 minus lambda. Right. So the product of the diagonal components is 1 minus lambda, 2 minus lambda, plus or minus I times I squared. I squared is minus 1. Then this minus here makes it plus 1, and this minus is minus 1. Okay, and it's equal to 0. All right. So let's expand the parentheses. 1 times 2, 2. 1 times minus lambda, then minus 2 lambda, and then plus lambda squared, and minus 1 equal to 0. It's equal to lambda squared, then minus 3 lambda, then plus 1 equal to 0. Is this even right? 1 times 2, 2. 1 times minus lambda, then minus lambda times 2 minus 2 lambda, and plus lambda squared. Let me see. Okay, it looks good. It looks good. All right, so lambda 1, 2 is equal to 3 plus minus square root of something like this, right? And divided by 2. So lambda 1 is equal to 5. I don't like this square root of 5. Anyway, yeah. So first of all, this lambda 1 and 2, they are real values. Real values, right? So by this we confirm the first property, and now we can go ahead and write the equation for the eigenvectors, which are our matrix C minus lambda 1, 2, identity matrix, and then multiply by the first or the second eigenvector, right? So for the first one, so we have 1 I minus I2, 1 I minus I2, minus, I don't like this eigenvalues, but I mean, okay, 1 minus 3 plus square root of 5 over 2, I minus I, and then 2 minus 3 plus square root of 5 over 2. This is the first one, times x1 x1a x1b equal to 0. Okay, so it is equal to 1 minus 3 plus square root of 5 over 2 x1a, and then plus I x1b equal to 0. And for the second one, do we get the same? No. Let me. Yeah, for the second one, we get minus I x1a, and then plus 2 minus 3 plus square root of 5 over 2 times x1b equal to 0. I don't like that these equations become so big, so it would be probably too difficult to show analytically that the the vectors are orthogonal, because then we will have to take the inner product. So probably, I'm not sure, but probably the problem that I came up was with 1 here. So maybe let me see, maybe I'm wrong. So maybe let us put 1 here. It gives us 1 here. So it gives us 1 minus lambda minus lambda and plus lambda squared. Then get lambda squared, then minus what's going on here? Let me oh yeah, one here, right? 1 here. Yeah. So then this one and this one cancel out. Here I have 2 lambda, and this one is gone. Okay. For this problem, it's much easier to demonstrate the point. So I can factorize this one like lambda times lambda minus 2 equal to 0. It means that lambda 1 equal to 0 and lambda 2 is equal to 2. Yeah, they still real valued, but much simpler to represent. I don't know why I put that 2 before. All right, so now it's much easier to represent. So for the first one, it is 0 here and 0 here. Okay, and let me clean this up. Okay, so it will be 1 I minus I1. Yeah, this is 1. x1a, x1b vector equal to equal to 0. So the first one is x1a plus I x1b equals to 0. And the second equation is minus I x1a, and then plus x1b equal to 0. And again, they are basically the same up to the multiplication by I, both parts, right? Yes. So we can consider just one and assume that the x1b is equal to 1, as usually we assume. That means that x1a plus I equals to 0 and x1a is equal to minus I. Okay, so the x1 vector is equal to minus I over, oh, sorry, not over the first component, second one is 1. Yeah, so it's much easier to demonstrate the point without this extra calculations. But this is the first vector. For the second one, right, we still need to write the second one. So the second eigenvalue is 2. Second eigenvalue is 2. It means that y minus 2. So 1 minus lambda second, then I minus I, y minus lambda second, x2a, x2b equal to 0. All right. So this is the equation for the second eigenvector. Equation for the second eigenvector. We substitute 2 for the lambda 2. It gives us minus 1 here, I minus I, and minus 1 here. X2a, x2b equal to 0. Okay. So the equations are minus x2i plus I x2b equal to 0. And the second is minus I x2a minus x2b is equal to 0. Again, they are identical up to multiplication by imaginary unit. We assume that x2b to be equal 1. And that means that x2a is equal to I. Very good. So x2 is equal to I1. So we obtained two vectors, right? And then to check that the vectors are orthogonal, we need to take the dot product of the two. So it's going to be x1 times x2 complex conjugate, because now the vectors are complex valued, right? So for the first one, for the x1 is minus I and 1. So I write this in the row, minus I1. And the second is the column with components I1, but complex conjugation is minus I and 1, right? Okay, and now the product minus I times minus I gives us minus 1, and plus 1 times 1 times 1 is 1. So it's 0 indeed. So the vectors are orthogonal. Yeah, for the initial vector with 2 here, you can use like Mathematica to check that the eigenvectors, they will be like more bulky, but they still orthogonal, and the eigenvalues are real values, real valued. Okay, and since these vectors are orthogonal, once again, one can use them to one can use them to span the basis, to represent the space using that basis. Okay, so the next property of the matrices, this is actually the introduction of a new type of matrix. It's called inverse matrix. Inverse matrix. Inverse matrix. I mean, this is by analogy, like if you have a number like 5, right? What is the inverse number? 1/5. Why? Because the product of the two gives you 1. Or the same for the vector. The inverse vector, like if you have a vector x, what is the inverse vector? Inverse vector is is vector itself over the length squared of the vector, right? Why? Because if you take the product of the two, you have vector times vector over absolute squared of the vector. So in the numerator, you get the absolute square of the vector, absolute square of the vector in the denominator, so it's 1, right? So this way, you can find the inverse vector to the initial one. But yeah, in what follows, we will need the inverse matrix. So inverse matrix is denoted by the matrix with this power -1 inverse matrix, and by definition, when I multiply this inverse matrix by the matrix itself, I supposed to get the identity matrix. So again, without the any derivations, let's write down the result for, I mean, like formula or procedure for finding inverse matrix. So yeah, by the way, the inverse matrix exists only if the determinant of the matrix is not equal to 0. So if it's in 0, then the inverse matrix exists. So if determinant of the matrix in 0, the matrix has an inverse matrix. And here is the procedure to find this inverse matrix. So suppose we have this matrix A with components A11, A12, etc., A21, A22, etc., and so on. Right, so this is the matrix. And by the way, the matrix also supposed to be quadratic because of the properties of the determinant. So it's supposed to be quadratic matrix. And the formula for finding the inverse matrix is as follows. So A inverse is given by 1 over determinant of the initial matrix A, and then times a matrix composed by -1 to the power of I plus j times the minors of the transposed matrix to the matrix A, such a construction. So as you can see, it's much more bulky, right, comparing to the vectors, or I mean, especially then to the numbers. But still, it's pretty. I mean, it's pretty easy to find if you have some practice. So let's consider an example then. So I use blue for examples. Example. So for the example, let's consider a matrix A with components 2, 3, 1, 2, for example. right? And the problem is to find the inverse matrix. What is the inverse matrix to this one? All right, so the very first step one has to do is to check if the determinant is not zero, right? So we need to find this determinant. So determinant of matrix A is 2 times 2 is 4, minus 3 times 1 is 3, 3. So determinant is 1. So the determinant exists, so exists the inverse matrix. So what is next? Next, we need to find the transposed matrix according to this formula. And the transposed is 2, 1, 3, 2. This is the transposed matrix. Next, according to this formula, we need to find the matrix of minors, right? So the first component here is 2. We cross out the first and the first row, the first column, we got the element 2. Then for the element 1, we get minor 3. Then for the element 3, we got the minor 1. And finally, for the 2, we got minor matrix of the minors. And finally, we just need to combine everything. So for the inverse matrix, we had 1 over determinant gives us 1. So I don't write 1. And then matrix. And this construction, minus 1 time to the power of I plus j, this is just, I mean, to set the, or to choose the correct sign before the minor. So for the element 1, 1, we obtain 2, 1 minus 1 to the power of 2 is plus 1, so it's just 2. Then for the 3, we get minus 3. Then for the 1, we get minus 1. And for the last one, 2 is 2. Yeah. So this is this is the answer. This is the inverse matrix to the initial one. And of course, let's check that this matrix is inverse. So it's, I mean, it's enough to take the product of the two, right? So the first one is 2 minus 3 minus 1 and 2, the first matrix. The second one is 2, 3, 1, 2, 2, 3, 1, 2. Okay. Okay, just remind you that the way we take the matrix product, right, the row by column, row by column, row by column. So for the first one, for the first element, first row, first column, we got 2 times 2 is 4. Then minus 3 times 1 is let me see, minus 3. Okay, for the second one, 4 minus 3, like right, for the second element, 2 times 3 is 6, then minus 6, right? Then for the third one is minus 1, 2 is minus 2, and then plus 2, and finally minus 3 plus 4. Okay, so 4 minus 3 is 1, 6 minus 6 is 0, minus 2 plus 2 is 0, minus 3 plus 4 is 1. So this is identity matrix in this space. So our solution is correct. And do you have any questions at this moment?
No, sir.
Very good. So then the example number 2, or the problem number 2. So now let's consider.
Professor,
Yes.
I'm so sorry. Could you scroll up just for like maybe 5 seconds?
Okay, so this example number 2. Let's consider the Hermitian matrix.
Thank you.
Hermitian matrix now A 1 I minus I 1, right? For example, the matrix that we just considered when we were talking about the eigenstates and eigenvalues. So what is the inverse matrix now? So for this matrix, we first have to define the determinant of this matrix, which is determinant of 1i minus i1, which gives us 1 minus I times I gives us minus 1. This minus is plus 1. So it's 1 minus 1 is equal to 0. So this means that this matrix doesn't have inverse matrix. Don't exist. Don't. So it's not good matrix for the inverse matrix problem. So let's consider another one. 1i minus I and 2. Instead of 1, let's consider 2 to make this determinant to be equal 1. So again, what is the inverse matrix for this one? Right. So determinant of this matrix now is, as we discussed, 1. So this is the 1. For the transposed matrix, we got 1 minus I 2. This is transposed matrix. For the minors of transposed matrix, we get matrix 2 I minus I and 1. Okay, and finally, for the inverse matrix, 1 over determinant is 1, and then for the first element we got plus, so it's plus 2, then minus I, then plus I, and then 1. So this is the inverse matrix. Again, let's check that this is really inverse matrix. We take the product of this one minus I1, and the initial one was 1 I minus I and 2. Okay. So 2 times 1 is 2 plus I to the power of 2 I squared is minus 1, so 2 minus 1. For the second is 2I minus 2I. Next, I minus I. And the last is I squared, which is minus 1, plus 2. Very good. So it's 1, 0, 0, 1. So again, it's identity matrix. The solution is correct. So important note about the inverse matrix. note about inverse matrix. So last week we discussed that a matrix can represent a transformation, a linear transformation of a vector in the space, right? Like a rotation, changing the length, etc. And if a matrix A represents a linear transformation, then inverse matrix represents the inverse transformation of the vector, right? So let's write this. If a matrix Oops, sorry. Do you hear me now? Anyone?
Yes, sir.
Oh, yeah, very good. I got disconnected for some reason. Yeah, I guess
No problem.
something happened to them. Yeah. So yeah, where was I? If a matrix A represents a linear transformation, then inverse matrix represents the inverse transformation. Inverse transformation. Transformation. Like for example, if a matrix A rotates the vector by minus 30 degrees, then matrix inverse matrix A minus 1 represents the rotation of the same vector by plus 30 degrees. So basically, inverse transformation. For example, yeah, if I have this matrix and this matrix acts on the vector x, and as a result, I get another vector y, I can multiply this by opposite matrix, inverse matrix A on the left, both sides, right? So I get A minus 1, A vector, and then it's equal to A to the power of minus 1, Y. Okay, so this is the identity matrix. Identity matrix times vector is just the same vector. So we get this result that the initial vector x is given by the inverse matrix A times y. Okay, so inverse matrix represents the inverse operations. Very good. The next one, the next property or topic or subtopic is very important. It's called unitary matrix. Unitary matrices. Matrices. Very important. Why important? Because in quantum, as we will see next week, all transformations of quantum system is represented by unitary matrix or a set of unitary matrices. And the way as a quantum computer works basically is described in terms of unitary matrices. So what are the unitary matrices? So for the quantum, we need matrices that don't change the scalar product of of two vectors. For example, in quantum, the scalar product of a vector by itself represents the probability of finding a system in a particular state, and we require this transformation this transformation doesn't change the scalar product of the vector by itself, and as well as the scalar product of two vectors. So we need matrices. We need matrices that don't change the scalar product of two vectors. You see, so this is the third lecture of quantum computing, and we still didn't basically tell a word about quantum. And so far, everything was about linear algebra. But without knowledge of this linear algebra, it's literally impossible to discuss quantum computing, quantum information theory. Even simple undergrad course of quantum computing necessarily based on linear algebra matrices, ket and bra vectors, operators, and we have to use to all these things basically. So unit matrices, as we said, they have to keep the scalar product of two vectors unchanged. So let's go ahead and write the product of two vectors. Let's write them in the ket bra notation, bracket notation. The first vector is A dash and B dash. By this dash sign, I mean the transformed vector after transformation, right? So the vector B, which we got after transformation, is written as the product of a matrix. Let's denote it by U, some U matrix, which transforms the initial B vector to the vector B dash, right? For the second one, for the second vector A dash, we write the same U. This hat denotes operator, by the way. So this hat denotes operator. It's a traditional way to denote an operator. If you write this without this hat, it's still okay, as soon as you understand what you are writing. So it's initial vector A. But we need the bra vector A, not ket. So we need to dagger this vector, right? I remind you that dagger is complex conjugation and transposition. So it's a Hermitian conjugation. So dagger, Hermitian conjugation. So when I apply this dagger, what I will get? I will get this vector A, because this is another reminder that vectors bra and ket, they connected through the Hermitian conjugation, through this dagger operation. For example, A dagger is equal to the bra vector A. Okay. And since this dagger, this Hermitian conjugation, is the subsequent application of complex conjugation and transposition. This transposition sweeps the things. For example, here in this part we have u times vector a, but after application of the transposition we have to exchange the position of the two. So it's gonna be vector a bra times times the matrix u dagger. Okay, and this is a little bit unusual, but this writing simply means that this operator u, this matrix u, applies or acts on the vector on the left rather than on the right. So this is the the property of bra vectors against the cat vectors. All right, so now we have this formula for the b. We can plug in this to this expression above, and for the vector bra a we also get one. So we substitute this and write a, then u dagger, okay, then u for the b, and vector b finally. Okay, and as I said, we require this scalar product of two vectors unchanged after this operation u. So we require these to be equal to identity matrix. Okay, so this must be identity matrix. If so, then as a result we get a times b, and the scalar product is unchanged. So, and this is basically the definition of a unitary operator. So u dagger times u is equal to identity operator. Okay, and if I multiply this formula by u inverse on the right, I will get what? I will get u dagger equals to u inverse. So these two formulas are equally important. Basically, they are the same. So unitary matrix keeps unchanged scalar products. Okay, and the unitary matrix is a matrix that is a Okay, I'm back. Let me. Yeah, something happened to my internet connection. All right. So, do you hear me now?
Yes, sir.
Anyone? Oh, yeah. Great. Sorry for. Yeah. So the internet connection today is seems to be unstable.
No problem.
Yeah, but the beauty of this online version of the lecture is that everything is recorded first, and second that I will be able to maybe re-record some parts of the lecture afterwards. Anyway, so yeah, so the definition of the unitary matrix, right? So the unitary matrix is a matrix that or which inverse version coincides with the Hermitian conjugation. So Hermitian unitary matrix equals Hermitian conjugation coincides with the inverse matrix. Very good. I will prepare a couple of problems for the next homework about this, because this is pretty pretty important.
Professor,
Yes.
I'm sorry, what does that say? Hermitian conjugation, what?
Coincides, right? Coincides. So basically, I'm talking about this formula here. So unitary matrix or unitary operator is the operator which inverse version coincides with the Hermitian conjugated, or vice versa. Hermitian conjugated coincides with the inversion operator. Okay, so this basically means that for a given operator which acts on a vector and creates another vector, and inversion operator does the opposite, right? It restores the initial vector, and the Hermitian conjugated basically does the same. So yeah, this is pretty important for the quantum, and you will get a chance to practice this in the homework. And for now, let me conclude this matrices part with the item number 10, right? And this topic of basically, so as we say that we have a matrix, right? And this matrix transforms vector from one to another vector. But if I do something to the basis, for example, I can I can apply the matrix, the transformation on the basis, and transform the basis, right? And of course, this transformation leads to the change of the vectors in that space. I mean, not the vectors, but the components of the vectors. And also, being applied on the matrix, it also changes the matrix. in the same, defined in the same space. And now I'm asking a question: how to transform an operator or a matrix from one basis to another one. And also here, maybe I need to make an important aside on operators and how operators are connected to matrices. So we already discussed several matrices, and you supposed to like understand how a matrix work, how it arranged, right? It's just a table of some numbers, real or complex. And today I also said several times this word operator, and without maybe discussing this. So let's discuss the concept of operator first. Operator. So operator, well, operator is something that takes one function or vector and creates another one according some rules, right? For example, for a function f of x, function x is argument or variable. I can, for example, take the derivative of this function by x, right? So this action, this part of derivative, can be considered as a operator. So the same can be written as something like L operator fx, right? So I just substituted this differential by the sign of, I mean, this letter of operator. And operators can be of different kind. It can be, for example, an integral of the function. It's another operator, which is integral operator. Something else. So in quantum mechanics, you probably remember that this differential operator is connected to the momentum operator in quantum mechanics. So operators important, and important point here is that any operator can be represented as a matrix. So any operator can be represented in matrix form. How we do so? So for example, for any arbitrary operator L, I can multiply this operator on the left and on the right by the basis vectors, like this, and consider a construction like this. So it's a n vector bra, then operator, and then another vector cat m. Okay, so, and after doing so, I will get a matrix with components, let's say, if I enumerate n and m like 0, 1, 2, and etc. So it's gonna be 0, L, 0. Next one is 0, L, 1, 0, L, 2, so on. And then 1, L, 0, 1, L, 1, 1, L, 2, and so on and so on. So it's gonna be a matrix like this. And any operator can be represented in matrix form. Okay. And this is kind of essential for the next. Key point to understand here is that operator itself can be presented, can be given as a mathematical operation, like derivative, right, or integral, or divergence, curl, etc. So it's a mathematical operation, and the way we present it as a matrix depends on these vectors n and m. So vectors n and vectors m are basis vectors. And different bases with different basis vectors will give us different matrix. This is known as the theory of representation. Yeah. And now we wonder how this matrix that describes the operator in the mn basis, how it transforms to another basis. For example, I decide to change my basis n and m to, maybe it's not correct to say basis nm. It's any vector from this basis is the basis vector. But when I change the basis, these vectors n and m, they became like other vectors from this from the new basis. For example, let's write it let's write it like this. So for example, for the vector m, right, after transformation of the basis, so this u now denotes the transformation of the basis. It can be unitary transformation, for example. So this transformation u that acts on the new vector m dash. So I just connect the basis vectors in the old basis and new one, right? And for the n, I get the same n dash. And now I need to write the bra vector n, which is n dash times u dagger. Okay. And now I substitute this to this formula for the matrix of the operator L. Okay, for the n, I get n dash u dagger, then this operator L, and then u operator, and m dash vector. And comparing the two, I conclude that the operator, right, it transforms through the this matrix, transformation matrix. For example, the unitary matrix U dagger L U. Okay, so once again, for example, in a chosen basis, you have a operator L with matrix NLM, and then you decide to change the basis to a new one. And to do so, you need to multiply the operator L from right and left side by this transformation operator U. So we can write this V transform an operator or matrix. The same holds for a matrix. By applying the operator from left and right sides. Okay. Yeah, so this is basically what I was going to tell you about the matrices, and this is the essential for the future. We might not use this transformation of the operators much, but the concepts of Hermitian operators, unitary operators, inverse operators, inverse transformations are the key points for the future. As a quick aside, let me also make a note about function space. Function space. Function, right? We used to use functions to represent, situations when something depends on other things, like temperature depends on coordinate, or the price of something depends on time, etc. And it turns out that we can use the linear algebra to describe such things. And let me give you an example to make it clear. So let us stay this way. So the functions can be orthogonal. Too, like vectors. Orthogonal functions, what it means. To introduce that, we need to introduce the concept of inner product of functions, right? Not vectors, but functions, like a projection of one function on another function. So it's a generalization of the inner product approach. So, for example, suppose we have two functions f of x and g of x, and the product of two functions is given by the integral of two functions, of these two functions, over some integration limits. So this is by definition the integral of the two. And we can also use this cat and bra notation to write the same in this form, G, F, like this. So we can use we can introduce the inner product of two functions, and we can also use this Dirac notation for the function products. And yeah, so basically the language is the same. And why it's important? It's important because if we take functions like fn x, again, this is the cat vector of a function, right? Something like 1 over square root of pi cosine nx, and another vector g n of x 1 over square root of pi sine nx, right? We know that the integral of sine times cosine is equal to 0, right? So we can write this bracket notation for the function j and the product with f, something like this. And it's always equal to 0, which means that these functions are orthogonal. And we can use these orthogonal functions to represent other functions in this space. So if we choose to work in this basis of sine and cosine functions, then we can represent any function as a vector in this space, and represent this vector as through projections on the corresponding basis vectors, right? For example, I remind you what we usually have for the vector space x, y, and z, and then we have this E1, E2, E3 eigen unit vectors, and then any vector in this space, say a vector, right? It's given by the sum of the projections of this vector on the unit vectors ai, summation over I, and the unit vectors I. Okay, so this is typical what we have in the vector for the vectors. We can represent the vector by its projections. And this property here, this fact that some functions can be orthogonal, simply means that we can introduce a function space with function unit vectors, right? For example, this f1 of x, f2 of x, g1 of x, g2 of x, and so on up to basically infinity. So this n here can be any number up to infinity. So this space becomes infinitely, the dimension of this space becomes infinite. So it's infinitely the space with dimension infinity. Okay, and then the other functions, like any other function of the same arguments a of x can be represented the similar way. It could be something like ax and then summation some constants an function fn plus some bn function gn, something like this, right? And the summation over n. So, and you probably recognize this. What is this? This is the Fourier transformation, right? Fourier transformation. Maybe the main, I mean, the most important thing in physics, in engineering, all these fields, Fourier transformation. The point that you can represent one function through the series of other functions. So, and the point, the fact that these functions here, the sine, cosine functions, they are orthogonal, allow us to represent any function as a series of sine and cosine function. You see, like how introduction these dimensions, this function dimensions, function space, allows us to represent any function also as a vector in this function space. And yes, well, so this is the generalization of a concept of a vector and the concept of a space. So we see that the space can be infinitely, the dimension of infinity, so infinitely large dimension. Okay. And this brings us to the final point of today's lecture. It's called Hilbert space. Hilbert space. This is where the quantum mechanics, quantum information appears. And let me put this exclamation mark here. So Hilbert space is the space in which the quantum mechanics, quantum computing lives and works, right? So this is basically the main space for us. So Hilbert space, by definition, Hilbert space is a complex space. In parentheses, let's write of infinite dimension, dimension, meaning that it can be, the dimension can be infinitely large, just like what we saw for sine and cosine functions. And another key point here is complex. So the space is complex. We use the complex numbers to represent the vectors here in the space. And let's also write with basis, and let's denote this basis like this psi n, like this. So let me draw this basis like this. for example. So of course I draw this basis on the plane. That's why these vectors look not orthogonal, but they assume to be all orthogonal to each other. So we cannot represent this on a piece of paper or even in 3D dimensional. In 3 dimension, this basis, the span of this basis can be infinitely large. And we just bear in mind that all these vectors, these basis vectors, like psi1, psi2, psi3, psi4, etc., psi n, and n can be infinite, infinity. So all these vectors are orthogonal, okay? And when we introduce this space, any vector in this space, like psi vector, we follow the tradition in quantum mechanics, we denote this vector psi. So psi vector in this space, it's an arbitrary vector. Arbitrary vector in Hermitian, in Hilbert space, and this vector, as we introduce these basis vectors, we can represent this vector through its projections on the basis vectors. So it's going to be Cn, summation, and basis vectors. Okay. So in quantum, we say superposition, superposition, meaning that for a given system, which can exist in different states, psi1, psi2, psi3, psi4, etc. So these are eigen vectors, eigenstates of a system. Okay. But the rules of quantum mechanics dictates us that before we measure the system, we have to consider the system to exist in all these states simultaneously at the same time. Okay. And we represent this state by psi vector. And this superposition principle dictates that we take into account all these basis vectors, psi1, psi2, psi3, psi4, etc., with different C1 or Cn coefficients, which are the projections of the vector on the basis vectors. We will discuss that next week in more detail, but yeah, but this is already kind of where quantum mechanics appears. And quantum mechanics is known as the principle of superposition, but mathematically this is just the representation of a vector, of this psi vector, through its components, its projections on the all eigenstates or on the basis vectors. All these words are the same. In this case, eigenvectors and basis vectors, they are basically the same thing. All right. So how we can find this projection Cn components? So we can multiply this expression by the psi m vector bra, and what we will get? We get psi m times psi, our vector, equals to, since summation runs over n, and our vector gets this index m So we can insert this vector into the summation and basically multiply each term by this vector Cn, and then goes psi m psi n, this bracket bracket construction. So now we use the fact that these these basis vectors, they are orthogonal and orthonormal, which means that this inner product here is equal to delta mn, right? Which is n on the main diagonal, one units on the main diagonal. And after summation, only the term with when n equals m survives, in it's equal to 1, so we get Cm. So for the projections, we indeed get this construction here, which denotes the projection of a vector psi on the corresponding basis vector. So it's exactly the same what we used to in the vector analysis. Okay, so this is the way how we obtain these components. And of course, now since we are in the Hilbert space, this psi, this Cm projections, they can be complex. They can be complex. And dimension can be any, even infinity. But in quantum, we start from much simpler case of two-dimensional Hilbert space. Two-dimensional Hilbert space. And let's put qubit here, because essentially two-dimensional a vector in the two-dimensional Hilbert space is already a qubit from the mathematical point of view. Okay, so we truncate a Hilbert space or two-dimensional two-dimensional case. So basically, we consider truncated version of entire Hilbert space. As we will see, this truncation is dictated by some physical properties of a system. For example, if a real quantum system consists of many quantum states, okay, sometimes in certain sometimes we can consider only two states of a system, and don't omit the others. Okay, and in this case, this system becomes a qubit, and it exists in the two-dimensional Hilbert space. So since the space is two-dimensional, any vector in this space is two-dimensional vector with two components. For example, vector A gets two components, A1, A2, right? What else? If I need the bra vector, I just take the dagger of the cat, and it gives me transpose conjugated, it gives me the bra vector A. Okay. If I consider something like this, the inner product of vector B and vector A, it's equal to A1, B1 complex conjugated. Okay, because A and B they can be complex. We consider Hilbert space, so these components can be complex. A2, B2 complex conjugated. Okay. This is inner product and outer product of the vectors A and B. Okay. What it is? It is A1, A2 times B1 conjugated, B2 conjugated, right? So it gives me the matrix with components A1, B1 conjugated, A1, B2 conjugated, complex A2, B1, A2, B2 conjugated. Okay. Yeah, so this is how we represent the vectors in the two-dimensional Hilbert space. And the last thing I want to tell you today is the basis vectors in this two-dimensional Hilbert space. The most simple, the simplest basis we introduce, the simplest basis is 0, 1. We introduce the basis 0 and 1. Okay, so what is 0, what is 1? We already mentioned that probably last time that vector 0 is given by components 1, 0, and vector 1 is given by components 0, 1. So it's the simplest basis ever. So these are two-dimensional vectors, and we can use them to represent the two-dimensional Hilbert space. But of course, we need to check that, right? We need to check that these vectors are orthogonal. So let's consider the inner product of 1 and 0. So the 1 gives us 0, 1 row, and the 0 column is 1, 0. Okay, so 0 times 1, 0, 1 times 0 is 0, so the product is 0 indeed. At the same time, the product of 1, 1 or 0, 0 gives us 0, 1 here, 0, 1 here. So 0 times 0, 0, 1 times 1 is 1. So the answer is 1. So indeed, these vectors 0 and 1, they are orthogonal and normal. They are orthogonal and normal, which means their length is 1. So we can use these vectors to represent any vector in the two-dimensional Hilbert space. Okay. For example, a vector would be as simple as just the superposition of these two basis vectors. Why not? We can take the first one plus add another one, and this is another vector in the in this two-dimensional Hilbert space with components 1, 0, 0, 1, which is 1, 1. But for the quantum, we need to keep all the vectors are normalized. So we need to normalize this vector. So let's define the length of this vector, psi, all right? I write for the first one 0 plus 1, dagger, okay, because this is this part, the bra. And for the cat vector, it is 0 plus 1. Okay, so applying this dagger, the Hermitian conjugation, it gives us 0 plus 1 times 0 plus 1. And it gives us 0, 0 plus 1, 1. Okay, because 0, 1, 1, 0 gives us 0. They are orthogonal. And as a result, we get 2, right? 1 plus 1 is 2. So in order to normalize this vector psi, so n, normalized, we need to divide by square root of this length, which is 1 over square root of 2, 1, 1. Okay. So this vector, I mean, this is also the same as 1 over square root of 2, 0 state plus 1 state. And this vector is interesting because it can be used as a vector of another basis. And this vector bears name of this plus, cat plus, is equal to 1 over square root of 2, 0 state plus 1 state, okay? So it's exactly the same formula, I just rewritten it here and give it a name plus. And this vector gets the second, the counterpart vector minus, which is the same, but the sign here, minus state 1. So this is another alternative basis that also very useful for the next. So this is basis called plus minus basis. Okay, and finally, I want to describe the outer product of two basis vectors, like 0, 0. It is equal to 1, 0, 1, 0, right? The product of the outer product of two vectors is given by 1, 0, 0, 0, and vector 0, 1 is equal to 1, 0, 0, 1, which is 0, 1, 0, 0. Okay. Next one is 1, 0. It's given by 0, 0, 1, 0. And finally, for the last one, the outer product 1, 1, it's equal to 0, 0, 0, 1. Okay, so it's interesting because I can use these outer products of the basis vectors to represent any matrix in this two-dimensional Hilbert space. For example, okay, A, B, C, D, simple two-dimensional. matrix 2 by 2. And I can represent this matrix using this Okay, so this is the result for representation of a matrix in two-dimensional Hilbert space through the basis vectors, right? So if you expand all these inner products, outer products, and multiply each one by A, B, C, D, the corresponding number, you will get this matrix. So you can represent any matrix 2 by 2 via these outer products of basis vectors. All right, so this brings us to the end of today's lecture. Let me press stop, and then we can. Yes.